Okay, so for this question, we actually saw one almost exactly like this in Pivot Interactives. So there's really two elements to this question. We've got an inelastic collision going on when the clay hits the block. It's a perfectly inelastic collision because it sticks. So we've got a perfectly inelastic collision over which we can assume momentum is conserved. And energy is not conserved during that collision, right? Because it's an inelastic collision. But energy is conserved during the swing of the of this pendulum thing, right? So we've kind of got to look at two separate portions of this. So let's first look at the collision. So in the collision, the initial momentum of our system, and I'm just going to call right the positive direction. The initial momentum of our system is little m v naught. And then after the collision, the objects stick together and move with some new speed that we don't know. So that is sort of the first part of our of our scenario. And then after that, energy is conserved during the upswing. So the kinetic energy of the squished clay and mass moving together at this new speed v, which is going to be slower than v naught actually, that kinetic energy is converted into gravitational potential energy. So I could say something like 1/2 m plus m v naught squared is converted into gravitational potential energy. Something like that. And we want to solve for h. So first thing, we need to actually solve for, I made a mistake. This shouldn't be v naught. This should be v, just v, right? That's the speed after the collision right there. But we don't know that v, it's not given. So we need to use this equation to plug in for that v and then solve this out. And we can actually simplify this equation a little bit first. Maybe I'll move the conservation of energy portion of this over here. So first, let's just solve for v using momentum. So if we do that, right, mv naught over big M plus little m equals v. So we're going to plug that in for v over here. And if I do that, I get 1/2 mv naught over big M plus little m squared equals g times h. And now I just want to solve for h. So if I solve for h, I get 1 over 2g mv naught squared over big M plus little m. That is equal to h. So there I go. There is my answer to this question. That's part A, assuming I didn't make any mistakes. Okay, so now let's look at part B. So for part B, it says the clay is replaced with a bouncy ball, and the bouncy ball is fired from the same launcher with the same speed, and it's asking how the impulse will compare when we switch with the bouncy ball. So let's maybe just think about it this way. With the clay, right, we've got some initial momentum in this direction. Let me kind of make this more clear. Let's just say part B. Maybe I'll make part A really small. Just kind of tuck it out of the way a little bit. Okay, so for part B, let's compare the two scenarios. So with the clay, we've got some initial momentum, and it's moving fast, right? So we could represent that initial momentum with, let's say, like a big vector. Oops. Right, maybe something like that. And then the final momentum of the clay after it hits So this is right after the collision, right? It would be basically just a smaller vector, still in the right direction, but slower, right? That's a weird looking arrow. Come on. Whatever, something like that. Now, if we think about the bouncy ball, right? Now, its initial momentum is actually the exact same as the clay. But the final momentum is going to be different because it actually reverses direction. So the final momentum of the clay is going to actually look something like this, right? Because it's bouncing back the other way. So what that means is if we look at the change in momentum, it's more for the bouncy ball, right? Delta P is greater for the bouncy ball. And we know that the impulse between, right, the impulse of the bouncy ball will be the same as the impulse of the block, right? Because they're equal and opposite impulses applied to each other. So there is going to be more impulse applied from the bouncy ball on the block than from the clay. Maybe one more way that we could think about this that might be even a little bit more intuitive is if we just sort of write out the equation, right? So if we look at the bouncy ball itself, or if we just look at the equation, right? If we say delta P is equal to PF minus PI, right? So, and we compare the two scenarios. So in the case of the clay, right? In the case of the clay, PF, right? This is a small positive number, and this is like a big negative number in the case of the clay. But in the case of the ball, PF is a negative number because it bounces back the other way. And that means that the difference will have a greater absolute value if this is a negative number. So you could try plugging in some stuff like that just to kind of get it through in your brain, but that's another way of thinking about this.